Welcome back. So we've been talking about Pollard row factorization, which for numbers of a certain size or numbers with a certain size of prime factor works very well. So if you want to pick off, say, all the factors of a number that have 20 digits or fewer or something like that, then Pollard row can be pretty efficient. But beyond that, you pretty rapidly hit the wall and stop being able to do very much. Today I'm going to talk about two things which are much less general than Pollard row, but that can still be used to factor certain numbers. So those things are Pollard p-1 and Fermat factoring. So by way of introducing Pollard p-1, I want to go back to something that we've talked about before, which is how you'd go about factoring a sort of general number. So again, when I say general number, I mean a number that you don't know anything about. So if it's someone's RSA key, you know it doesn't have any small prime factors, so you don't bother looking for those. But for a general number, you don't know that. So here's a general 51-digit number that we don't know anything about. We've just randomly chosen this particular n. And as we've talked about, one of the first things that you can do if you want to factor this kind of number is calculate its GCD with some big factorial. So in this case, we see that we pull off a factor of 376,000 by taking this GCD. And this 376,000 number, it is the product of all the prime factors of n that are less than 1,000,000. So in this case, we have a 2, we have 3 3s, and we have a 6,967. So those are all the quote-unquote small prime factors of n. They're all the ones that are less than 1,000,000. So I'm going to go ahead and divide that 370,000 number out from our n, and I'm going to call the result n2. So n2 is n, but with all the small prime factors pulled out. Note the ZZ there around the division is just to tell Sage, hey, after you do this division, you're still going to have an integer, so I want you to think about it as an integer and let it do integer things. If you divide, it will automatically assume that you've turned it into a rational number, and it will rightly assume that you want to do different kinds of things with rational numbers than you do with integers. But this may frustrate you and cause all kinds of errors, so this just keeps it there. It's ZZ because the mathy way to write the integers is that sort of blackboard bold Z that you have seen in LaTeX and assorted places. So what Pollard p-1 is going to do is to extend this. It's going to give us a way to pull out yet more prime factors from now what's left here in n2. And so this is the calculation I'm going to make. And so what you see doing this is that by calculating this GCD, I've found another larger factor, namely this 1.5 trillion number, and you can see this 1.5 trillion number actually happens to be prime. Now, it is perfectly reasonable for you to ask, why on earth did you do this combination of things? And I want to show you why this worked. And so we've got this particular number, n, or n2, or whatever you want to call it. And we have some prime dividing n. And in this case, our prime is this giant 1.5 trillion-ish number. And I want to explain what we actually calculated and how we were able to pull out this factor. So what did we actually calculate? We actually calculated the GCD of n and 2 to the million factorial minus 1. Now we calculated this number here, mod n. That's the only reason why this number was at all reasonable. And so this GCD happened to work out to be p. That's what we found. So I want to understand why this GCD worked out to be p, and it's going to turn out it's something special about p. So to understand what's happening, I want to look at this number, mod p. Okay, remember, here I'm looking at something mod n, but p divides n, so I could just as easily look mod p instead. So what is 2 to this giant power minus 1 mod p? Well, if you think what actually happened here, you actually know what it has to be. It has to be 0 mod p. Because otherwise, this number wouldn't be divisible by p, and the GCD wouldn't work out to be p. So somehow this ends up being 0. And so the question we really have to answer is, why is this 0? And that's the same question as just asking, why did it happen that 2 to the 1 million factorial happened to be 1 mod p? Well, I actually know something about powers mod p being equal to 1. Namely, we know 2 to the p minus 1 is 1 mod p. That's always true for primes. This was just Fermat's little theorem that we started way back at the beginning of the class. And so, if this is already 1, every power of this is 1. And so what's actually happening here is that this is true because p minus 1 divides a million factorial. Just to reiterate, what am I saying? Since I already know from Fermat's little theorem that 2 to this power is 1, well, 2 then to any multiple of this power will also be 1. And so, in fact, the reason why this has happened, this rather remarkable coincidence that allowed us to factor this piece out of n, is that p minus 1 actually does divide this number. Now, let me go ahead and show you that in Sage. I have gone ahead here and labeled p as this number. And so what I want to do to show you what happened here is to factor p minus 1. And so what you see here is that all of the prime factors of p minus 1 are smaller than a million. And so they all go into a million factorial, and so, as claimed, p minus 1 does in fact divide a million factorial in this instance. So what's really happening here is that instead of only grabbing all of the primes less than a million, or whatever cutoff we happen to have chosen, we're grabbing all the primes less than a million and all the primes where p minus 1 only has prime factors that are less than a million. So we've sort of gotten an additional tier of prime numbers. Namely, those where p minus 1 is smooth, meaning has only small prime factors. So, just to see how this works in a few random cases, I'm going to have Sage generate us a few random 100-digit numbers, and then I'm going to have it, for each of those 100-digit numbers, tell us, first, what the GCD of the number is with a million factorial. So that is, what's the product of all of the factors of this random number that happen to be less than a million. Then, I'm going to calculate this GCD of 2 to the million factorial minus 1 with n. And I'm also going to do that with 3 to the million factorial and 5 to the million factorial. Why am I doing it with 3 and 5 as well? Well, Fermat's little theorem works equally well for any number in the place of the 2, so we might get slightly luckier in one case than the other. And so the real reason I'm doing this is that if I only used 2, this would actually look kind of unimpressive because it would miss the power of 2 that divides n. Because in particular, this number is odd, and so this GCD will never pick up on any 2's that divide n. Now, we handled that before by pulling out the small factors first. Now I just want to show you how this works. Now, note for a lot of these, all of these numbers are the same. So for this n that I showed you, the GCD with a million factorial was 61. So that was the only prime factor of n that happened to be less than a million. And it was also the only prime factor where p minus 1 was only divisible by primes that were less than a million. On the other hand, if we scroll down, then we see some numbers where we actually grabbed some rather large things compared to just grabbing the primes that were less than a million. So in this case, for example, the only primes that divided n that were less than 1,000,000 were 2 and 3, which is why we see a 6. But then this Pollard p-1 goes ahead and picks up these extra prime factors that I have highlighted, and so we get this enormous additional payoff that we can factor out of n. Now, here's just another 10, just so that you can have some more baseline comparison. Note, for this particular number, we did not find any factors at any point along this adventure. And so what may well be the case is this number might have been prime, or it might just have only had really large prime factors. On the other hand, in this case, you can see we actually found a huge number of additional prime factors. So the moral of the story here is Pollard p-1 is not a very good general-purpose factoring algorithm. In other words, you don't want to try and factor a number using only Pollard p-1. But Pollard p-1 is a good extra step to do at the very beginning, right after you've taken the GCD with this giant factorial, because you can also use that giant factorial to go ahead and grab some extra prime factors that have this special form that p-1 is smooth. Now, is this of much use when you're trying to factor someone's RSA key? Well, I've put here a fairly large RSA key. And we could just try this. And you see in this instance, we actually factor this RSA key right away. Now, this actually tells us something that's pretty important, which is that this was a very bad choice of RSA key for whoever's RSA key this was. Why was this a poor choice of RSA key? Well, it was a poor choice of RSA key because even though the primes are fairly large, not large enough for actual cryptographic purposes, but large enough that this number should be more difficult to factor than this, well, we've left the door open for someone to just luck into this factorization via Pollard p-1. Why is that? Well, even though this is a 30-digit prime, when you factor p-1, you see this has all kinds of small factors. And so, in fact, this would even have gotten picked up with much smaller than 1,000,000 factorial. I could have gone down as far as something like 15,000 factorial and still found this number with Pollard p-1. So, in other words, a prime being large is not enough to mean that that is a good prime to use for RSA. You also have to do a few other checks, like you have to make sure that p-1 doesn't have a bunch of small factors like this, because if it does, well, then it's going to break very easily to someone who looks at this. As a way of introducing Fermat factoring, I want to imagine that our goal is to factor this particular number. And I want to imagine that, for whatever reason, you happen to make this calculation. Now, at first, this might seem like a random curiosity, but I want to convince you, hopefully, that actually if you made this observation, that's good enough to factor n. So let me summarize what we just calculated. Have n here is some giant number that starts with 31. I'm going to go ahead and let x here be this 1, 2, 3, ... number. And y here be 11. And so what we observed with the calculation we happen to make is that x squared is congruent to 11 squared mod n. Now, I want to show you how knowing this fact is enough to factor n. So I want to break down this equation and write what it really means. So I'm going to bring the 11 over. Okay, so if I bring the 11 over, I get x squared minus 11 squared is equal to 0 mod n. So that means n divides x squared minus 11 squared. And so via our difference of squares factorization, this number n divides the product x minus 11 times x plus 11. This is all, again, as just a direct result of the fact that we observed that if you square x mod n, you get the same thing as if you square 11 mod n. Now, what this means is that every factor of n is either a factor of x minus 11 or it's a factor of x plus 11. And so what we can do is we can actually use our friend the GCD to break up the factors that are in common with x minus 11 and the factors that are in common with x plus 11. So that is to say, I'm going to calculate the GCD of n and x minus 11 and the GCD of n and x plus 11. So let's bring back up Sage and do that. And this GCD of this number minus 11 has gone ahead and spit out a factor of n. If instead we had taken x plus 11 and calculated that GCD, we'd have gotten the other factor of n. And I'll leave it to you to check that both of these factors I've listed are in fact prime factors of n. So this is all sort of magical and was all sort of based on the fact that I had observed that if I took this particular x and I squared it mod n, I got something that was readily observed to be the same as 11 squared mod n. But here's the general version of Fermat factoring. If I happen to find two numbers that square to the same thing mod n, then the GCD of n and the difference of those two numbers is a factor of n, and the GCD of n and the sum of those two numbers is a factor of n. Now, what's possible, the bad case, the nightmare scenario, if you will, is that actually one of these factors is 1 and one of them is n. But often, as you have seen in the example we just did, that's not what happens. Often, the factors of n are split between these two pieces, in which case then we successfully factor n. So I want to give us a second to figure out what's really going on here. Because actually, if you think back to stuff we've talked about before, we can actually piece together exactly what's happening with this algorithm. So let's look at, and I'm just going to pick 121 like the last example, mod some number n, which is a product of two primes. And I'm not attached, they can be any two primes, they don't have to be the ones from the example. Well, my question is, how many square roots does 121 have, mod n? Well, I know two of them. Namely, 11 and minus 11 are always going to be square roots of 121 mod any number, because they're square roots of 121 in Z. But, in fact, if you look back at the example, what we did was really to find an extra square root of 121. And if you think back to the Chinese remainder theorem, we actually know that there are two more square roots of 121, and in total, there are 4. And where do we get the 4 from? It's because the square roots are plus and minus 11 mod p and plus and minus 11 mod q in any of the 4 combinations. So plus plus gives me 11, minus minus gives me minus 11, and then plus minus and minus plus, the two mismatched combinations, give me two other square roots, two genuinely new square roots of 121 mod n that don't actually match with any of the square roots that I previously knew. So if you want to see that in the example we just did, we can go ahead and take our x, and we can mod it by one of our prime divisors, and you'll see that we get minus 11. It'll take you a second to see that that's minus 11, but that's definitely minus 11. And if instead we look at this number 1, 2, 3, blah, 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 our x, if we instead look at our x mod the other prime factor, then lo and behold, we get plus 11. So what happened before was that we had an x that was plus 11 mod p and minus 11 mod q. I'm just here thinking of p as the smaller prime factor and q as the larger one. And so this combination here means if I subtract 11 from both sides, well, then I get that x minus 11 is 0 mod p, but it's actually minus 22 mod q. And so what does that mean? That means that p divides x minus 11 But q does not divide x minus 11. And so that means when you take the GCD of x minus 11 with n, you find the factor of p, but not the factor of q, and so this GCD works out to be exactly p. And likewise, if you take the other GCD, you get exactly q. Now, all of this is predicated on the idea that I started with two numbers that square to the same thing mod the number I'm trying to factor. And that's, as it would happen, unfortunately not a very easy thing to find. And so this really only works if you somehow are lucky and find that combination. And I'll note, the obvious combinations don't work. So for example, if I take x and y to be the same thing, well, then when I take x minus y, I just get 0, and that's not super helpful. But similarly, if I take y to be minus x, well, then when you calculate this all out, it also does not help. So the only way that this actually ends up working is if you find a number that squares to the same thing as x, but y is not plus or minus x. So if I find two numbers that square to the same thing and aren't plus or minus each other, then we immediately factor n. Now, sometimes you might just luck into that, in which case then you can factor n. But one of the reasons I bring this up is because the best factoring algorithms are based on this idea. And so, for example, you'll often hear me talk about the quadratic sieve, because it's probably the best factoring algorithm that we know for applying to sort of big numbers. And what the quadratic sieve is essentially a combination of really three tricks to help you find pairs of x and y that square to the same thing. So the quadratic sieve has as its endpoint producing an x and y with this property so that you can factor the number. But it has to go through a number of clever steps to make doing that computationally feasible. But, in fact, after it does do that, it actually ends up being much more efficient than Pollard row. All right, that wraps up everything I have to say about factoring. In the next section, we're going to start talking about solving Diophantine equations and elliptic curves. I'll see you next time.